To make this program more applicable, we are going to convert it to a function. So we create a new function named capital PSO, which receives two arguments. One, the problem, and the other is the params, and returns some output. Okay, let's copy these codes from the initial implementation to the function PSO, and we assume that problem contains the definition of cost function nvar, varsize, varmin, and varmax. So the cost function is problem.costFunction, and nvar is the problem.nvar. And the var size can be created by the nvar itself. The varmin is the problem.varmin, and this is the problem.varmax. Okay, and let's align these comments. This is the problem definition part, which the first argument, the problem, contains everything needed to define the optimization problem. The next argument, named params, contains the parameter values for this algorithm. So the params, the maxit equals to params.maxit, and npop equals to params.npop, the population size. This is the params.w, params.wdamp, the params.c1, and params.c2. Okay? And everything needed is passed to the PSO using these structures, the problem and params. The other parts of the algorithm remain the same, and the algorithm runs, and if we'd like to turn off this one, we can add another parameter, for example, as params that show iteration information. It's not needed at all. You can comment this line, or you can pass a value inside the params structure to turn off this line of code according to the value of the field. And at the end, as an output, we return the global best, and we return the best costs, or maybe we return the population, the whole population. With the name of pop or particle. Also, we can rename the global best with the best solution, if we'd like. If other information is needed, it can be incorporated in the output structure as well. Okay, let's add the parameter for the turning off or turning on the display iteration information, and let's assume that show iteration info equals to parameters dot show iter info. Let's make it shorter. The flag for showing iteration information. This is the comment for the line of code. And if this is true or evaluated to true, this will show. Okay, let's save this function as PSO. the function cannot be saved to the same name, let's rename the PSO to PSO1 and save this as PSO.m. Okay, we can now modify this program to use the function PSO instead of implementing the mechanism of particle swarm optimization inside this script itself. Okay, let's define the problem cost function, the problem nvar, and this is not needed, and the problem.varmin and problem.varmax, and we can arrange these comments. This is the definition of problem. The parameters of PSO are also params.maxit, params.npop, and params.w, params.wdamp, params.c1, and params.c2. And we'll remove these blank lines, and params. The extra parameter show iter_info equal to true. Show iteration, the flag. Okay, this is the set of the structure of parameters, and it is passed together with the problem into the function PSO. Calling PSO. We'll remove these lines as well. And we'll call the function PSO with the structure problem and params. And the best costs is defined inside this structure, and the best sol also is defined inside this structure. Okay, let's run this program, the PSO1, and you'll see that this works fine. You'll see that the function works fine, exactly same as the previous script. Okay, so we converted the application to a function named PSO, which can be used to solve any kind of optimization problem, which is formulated as a minimization problem. You can turn off the iteration information, setting it to false, and if you call PSO1, it does not display anything, but the algorithm runs. However, I turn back it to the true value. It seems that the implementation of particle swarm optimization is finished. However, some minor bugs there exist in the implementation. For example, if we set the varmin or the lower bound of decision variables to a value, for example, 3, the search space does not contain the origin, and run the algorithm, we will see that the PSO converges to the origin again. So the PSO does not make attention to the lower bound and upper bound of variables, and this is not good. We will need to take care of the lower bound and upper bound of variables. This can be carried out after the updating of the positions of particles, and we should apply the lower bound, upper bound limits. So the position of particle I should not be less than the lower bound. So the maximum of this position and varmin is the result. If the position is greater than varmin, it's okay. Otherwise, if the position is less than varmin, so it should be corrected, and the varmin is considered. Similarly, for varmax and the upper bound, we can write this code as minimum of current position and var max. These two lines of codes apply the lower and upper bound limits to the position of particle. Let's run the application, PSO1, and you'll see that this is the correct result. All the values are 3, and this is okay. Okay. Another mechanism introduced into the PSO is the mechanism of limitation on the velocity size. And we should define a maximum velocity, and we should limit the velocity to remain inside the defined limit. We can define the max velocity as var max minus var min. However, this is a very large value, and it's okay to divide this value to 5 or times to 0.2. It's okay. Or we can write it as 0.2 times var max minus var min. Also, the min velocity is the minus max velocity. And all velocities in the PSO should remain in this range. We will do this by adding a similar bounding or clamping mechanism to the velocity itself. So we will velocity limits, apply velocity limits, and the particle I dot velocity is max of particle I velocity and min velocity, and for the upper bound we use the max velocity. So the velocity limits are also added to the implementation of PSO. For the parameters of PSO, there is some predefined good configurations. One of the well-known configurations proposed by Clark and Kennedy in 2002 is known as the constriction coefficient. And this is defined by these equations. Clark and Kennedy in 2002 defined the constriction coefficients, which is defined as, let's define a parameter named chi, and this is 2 kappa over the absolute value of 2 minus phi minus square root of phi squared minus 4 phi, where kappa is a value between 0 and 1, and it is commonly set to 1. And the phi is summation of two other values, phi1 and phi2, which is greater than 4. Commonly, these values are used. Kappa equals to 1 and phi1 equals to 2.05 and phi2 equals to 2.05. The constriction coefficient rule tells that W should be set to chi. C1, the acceleration coefficient for the cognitive component or personal acceleration coefficient, equals to chi phi1 and C2 equals to chi phi2. For this default set of variables, it can be computed, and we'll compute this using the MATLAB, and we'll use these values to run the PSO algorithm. Okay, let's make a copy of this script, and let's define the phi equal to 2.5, kappa equal to 1, and phi2 equal to 2.05, and phi, which equals to phi1 plus phi2, and chi, which equals to 2 times kappa over the absolute value of 2 minus phi minus square root of phi squared minus 4 times phi. And then we use to define the W as chi, and W damp. There is no damping in W in the constriction coefficient settings, and the C1 is chi times phi1, and C2 is chi times phi2. And let's save this as PSO2. Let's create a breakpoint and run the algorithm up to here. Kappa phi equals to 4.1 and chi equals to 0.7298, and W equals to chi, C1 equals to 1.49, and C2 equals to C1 1.49. Let's run the PSO using these settings. Okay, let's terminate the application and change the lower bound to its default value, also in PSO1. Also, let's increase the number of unknown variables to 10. And let's run the algorithm, PSO2. And this is okay. Without damping, the constriction coefficient works well. And the result for a 10-dimensional optimization problem is very good. Okay, the implementation of particle swarm optimization in MATLAB finishes here. We implemented the PSO as a script and then converted the PSO into a function and created scripts calling the function, the PSO function, and then we introduced the constriction coefficients. Let's comment it here. And this concludes this video tutorial. As mentioned before, this implementation can be used to solve various kinds of optimization problems or any kind of problem that can be stated as an optimization problem. You can modify the program and add some extra features introduced in the enhanced versions of PSO, in modified versions of PSO, since its introduction by Kennedy and Eberhard. Hope this was helpful to you. To be updated about newest items published on Yarpiz, You can follow us via Yarpiz website and official web pages of Yarpiz on Facebook, YouTube, and Google+. Good luck.